Okay, so as written here, my name is Norbert EICKER. I'm speaking here on behalf of the DEEP series of projects, which are in total by now 3 projects. So we started with DEEP, the DEEP Exascale Entry Platform project. Then we continued with DEEPer, and you might guess what the name of the 3rd project is. Well, it's DEEP-EST. So these are with colors the partners which are in DEEP-EST, and so there are also this with less colors partners which were involved in the predecessor projects, so in DEEP and DEEPer. As I said, in total a series of now 3 projects, so-called EU Exascale projects, so projects which shall prepare the EU to reach exascale at some point of time. In total, we had 27 partners in the projects, total budgets with some significant EU funding. So we started in late 2011, and so currently the plan is to run the projects until sometimes in 2020. So I'm from the Jülich Supercomputing Center, which is part of the research center of Jülich. So this is a real view of the Jülich campus, and we are located somewhere here, so where the institute is. So Jülich is the biggest research center in Germany, with a total of around 5,000 people working there. Jülich Supercomputing Center, we are about 200 people, and we are one of 3 national supercomputing centers in Germany, besides Stuttgart and Garching. So this is our mission. So the main aim of the institute is to provide compute power to German and European scientists, so to European scientists via PRACE. The 3 national centers in Germany are combined to a kind of virtual institute, which is called the Gauss Center for Supercomputing, which is then member in PRACE. So besides providing the infrastructure, other aims of Jülich are especially the co-design with users in vendors in order to find out how the next generation of supercomputer, which shall then go into production, shall look like. And so you can see this DEEP series of projects as part of this activity. So in principle, in order to get computer time in Jülich, you have to write a proposal, which is then peer-reviewed on the one hand side on a technical level, but most important on a scientific level, in order to find out if it's worth to fund this proposal, and then you get computer time assigned and can run on our system. So this right now occurs on different levels. So we are embedded in Germany in a larger structure called the Helmholtz Association. So if you're a scientist in Helmholtz, there is a special track where you can apply for computer time. If you're just at a German university, there is a different track running through the Gauss Center. And then if you're a European scientist, there is a track running through PRACE. So these are mainly the 3 tracks in order to get computer time. So once you were provided with computer time, you will run on one of our 2 big systems. So one is called EICKER and one is called Eureka. So EICKER is a BlueGene Q system, and as you can see that there are fewer projects, and our goal is that these highly scalable applications, so which have say less requirements towards the capabilities of the processor, so which are able to run on a BlueGene processor, but on the other hand can scale out and can make use of many processors. So this shall run on the BlueGene system, and all the other projects which are maybe less scalable or need higher single thread performance, these will be assigned to the Eureka system. So this slide just shows how the different application fields are distributed on the systems, and you can see immediately that for example, particle physics takes a major share of the Euclidean system. Well, so this seems to be natural since the blue gene systems were developed with lattice QCD in mind. So this fits quite nice. On the other hand, you might see that for example, biophysics basically runs on Eureka, since their applications are not that scalable and not as appropriate for Euclid. Okay, so as you can see, we have two types of systems. So currently still the blue gene Q system and the Eureka cluster. We run this dualistic approach, that's how we call it, since about 2004 right now, when we started with a single cluster, which at that time was built out of Power 4 nodes, so quite heavy nodes with 32 processors at that time. But we quite early found out that this setup is not able to suit all our customers or all our users. And so we started with even before this U-build system here, with some earlier BlueGNL system. And so from that point of time, it developed that we have this dualistic approach. So have on the one hand side a highly scalable system, which turned out to be BlueGene all the time. And we have this, what we call the general purpose supercomputer system, which are in the meantime cluster system, so starting with Europa, which was our first Intel Xeon cluster. Okay, so why are we having this dualistic approach? I already tried to motivate that this is due to the fact that, we have different type of applications, but let's take a more theoretical view on that. So let's talk about concurrency tails. So let's really start at the very basic level. So you all know that so in order to determine the speed up of a code or running on a parallel system, that there is Amdahl's law. So let's start with some notation. So we are interested in the speed up on n nodes or n cores compared to a single core. So we have in total n parallel cores, and then within your application there's a portion that can be only computed sequentially. This is what we call S. So S is somewhere between 0 and 1, and then there is a portion that might be computed in parallel, which we call P, and then it's obvious that S is equal to 1 minus P, right? So and then Jean Amdahl found out that the very basic scale-up property looks like that. So the scale-up that you can achieve is it's 1 over and then S plus P divided by N, right? So which basically means so that there's a sequential part which you cannot parallelize, so which is basically constant, but you can reduce the amount of time required to compute this parallel part P by throwing in more and more cores and basically reducing this this part of the sum. So if you then throw in larger P's for different S, then you will find out. So if you say have a parallel portion of 50%, then obviously you can, by throwing in more and more cores, you can reduce this to 0, which means that you have this 1/2 here, which in essence means the maximum speed up you can get independent of the number of cores is 2. Which is not that impressive. And even if you have a parallel portion of 95%, the maximum speed up you can get is 20. This is what we call strong scaling, right? To visualize this in a different way, so if you have a code which runs some part sequentially, then some part which is parallelizable and then a sequential part again. So if you throw in a second processor, you can halve the amount of time you require for this parallelizable part, and if you throw in to extra processor, you get even a quarter. And if you throw in an infinite number of processors, well, you can reduce this to 0, but what remains is a sequential part. So that's basically how it works. And now you can raise the question, well, we have this blue gene system with 500,000 cores, and there are applications which scale on the system, so how does it work? So, well, obviously, this cannot be strong scaling. And so the theory behind that it was developed by this guy, which is John Gustafson. So the important part is that unbulk keeps the workload fixed. So, well, this is strong scaling, but actually nobody really does on huge systems strong scaling, but the so-called weak scaling. So what you actually do is that you look at a kind of fixed time and that you modify the work to be done. And what you typically do is that the parallelizable part of your code is increased, right? So you keep with a sequential part fixed and just increase the parallelizable part, so which means that you increase the problem size basically. And then if you assume that S keeps constant, and if you put in all the formula, then you will find out that looking at the scale up, which is now the work done on n processors versus the number of one processor, and if you then actually increase the amount of cores and at the same time the amount of work to be done, then the scale up is not bound at all. So to visualize this in a different way, so what you actually do, if you throw in a second processor, you also double the work done in the parallel part, and well, this continues, and so then still the speed up is not ideal, but nevertheless, so if your sequential part is significantly small, then you can scale up also the application significantly. So which now brings us back to discuss scalability in a more general way. Well, we see in Jülich that you can scale applications to 500,000 cores, which we do on our Blue Gene system, and we have, I guess, in the meantime, about 30 applications which are in a member of the so-called HiQ club. So which are applications which have shown that they can scale on to the whole Blue Gene systems. And so we have some applications which can do that. And so if you look into the details, you see that most of them have some kind of sparse matrix vector codes and quite regular communication patterns. But of course, we also have this Eureka system, so the general purpose supercomputer, and the aim for that is to handle all the applications which really cannot scale up on this Blue Gene type of system. So which have less regular control flows or less regular memory accesses, so which require higher single thread performance, where the communication patterns might be more complicated. And well, the side effect is that typically these applications also are not that capable to actually exploit accelerators. So if you look into further details for this class of application, you will find that that these are applications which have code parts which might be scalable, so which might fit to some kind of Blue Gene system, but which have other parts which limit the scalability of these codes. So, and which then kind of bound these type of codes to this cluster system. But since these applications have this mix of code parts, So it's an idea which immediately comes up to look at heterogeneity for that. And so one idea is to optimize these different concurrencies of these applications in a way that you put them on the most suitable hardware. So to kind of tear these applications apart and put some of these on a Eureka class of system and the other part on a EICKER part of system. So if you look into multiple concurrencies, let's assume that you have two concurrency levels, so one called K, one called N now, right? So we move on and get away from Amdahl, where you have just sequential code and parallelizable code, but now we assume that we have code which is highly scalable, so which is quite easy to parallelize, and there are other code parts which are more sequential-like, but still parallelizable, but parallelizable to a different concurrency level. So, and this is what you see in many applications, especially in applications which couple different type of sciences, right? So, if you couple, say, fluid dynamics to some structural dynamics or stuff like that, and then if you put in some numbers, say that you have a part which is highly parallelizable and another part which is less parallelizable, then although so that there's only 50% which is highly scalable, you can still, by throwing in significant numbers of processors for both sides of the system, something like a speed up like 20,000 or that, and there are different examples. So what's important here is this factor F, actually, which is a kind of power indicator for the, compute power indicator for the different platforms to use. So the idea is that this highly scalable system has some basic compute power per core, and that you have a more capable processor on the other side. And so the ratio of processor powers is given by this factor F. So we have to talk about heterogeneity in systems. And so let's start with how this typically works today, and so how is a heterogeneous cluster set up today. So what you basically have is some kind of InfiniBand or omnipath network here, and then attached to it some cluster nodes, typically some Xeon processor, basically a more or less flat IB topology, so maybe a full fat tree or maybe pruned at some level. And management of resources is pretty simple because it's quite homogeneous. And then you attach to each and every cluster. So this stopped working. You attach some kind of accelerator, so typically something like a GPU. And but what does this mean for the management of resources? So since this assignment is static, basically at the time of procurement, you have to decide, so what is the ratio between CPUs and GPUs? And this, of course, brings you into a dilemma due to the fact that, well, there are applications which can profit from accelerators. So, and these might be happy on these type of nodes. So at least if the ratio between GPU and CPU power is chosen correctly. But of course there are different applications, and so there might be application which might benefit from even more GPUs, which means that they kind of starve from the limited amount of GPUs. On the other hand, there are applications which cannot profit from GPUs, so which means that they will basically use the Xeon processor, so the host processor here, and so this means that there are sitting resources which are unused, so which is also not nice. And if you look more into the details, so the key problem is that accelerators are not capable to act autonomously, right? So what you actually want to have is an architecture which looks more like that, right? So you have different resources, and you attach all the resources to some kind of fabric, hopefully a homogeneous fabric if this is possible. And if you have this type of setup, you can, if an application starts, you can assign the required resources to this application. So if there is an application which solely runs on these cluster nodes, you just assign cluster nodes. If there is an application which might run just on these accelerated nodes, so say an application which scales on BlueGene, you might just assign these accelerated nodes. But if you have an application which requires a mix of cluster nodes and accelerated nodes, you can assign any ratio to that. Well, so first question there, of course, is, but if I have this type of accelerated application, doesn't it suffer from the fact there is a network in between? Well, yes and no. So if you're sensitive to latency, this might hurt you, but if it's just bandwidth, it actually does not hurt you, because if you look into the details, well, if an accelerator is assigned or attached to a host CPU, you will use the PCIe bus. And if you look at the speed of a PCIe bus and of a fabric, typically you will see that the speed of the fabric is actually limited by the PCIe bus, but not by the fabric itself. So, for example, Mellanox could easily build a faster fabric, but they will not be able to attach it to a host CPU, since there is a speed limitation by the InfiniBand. So, which means that if we are able to have an accelerator which can act autonomously, we could set up an architecture like that. And with that, we can do this dynamical assignment of cluster nodes and accelerators. And as a nice side effect, we have the ability to offload more complex kernels. What does more complex mean? Well, it means that we might offload parallel kernels. Since these accelerators can act autonomously, you could even think that accelerators can do communication to each other without including a host processor. So that was the basic idea when we started with DEEP. So, and this is what came out in DEEP. Well, so this architecture is outdated, but it shows quite nicely what we have done there and what is the basic idea behind this cluster booster architecture. So you have this cluster, which is a simple InfiniBand-based cluster with Xeon nodes attached to it. And then we have a second cluster built out of accelerators. So in DEEP, we used the Xeon Phi processor at that time, so KNC. And since KNC was actually not self-bootable, but we had some dirty tricks in order to make it self-bootable. But in order to do these tricks, so we had to use a special fabric here, which is the Xtol fabric, developed at University of Heidelberg at Professor Brüning's group. So which means it's a European fabric, which is also quite nice. It's a 3D torus topology and has basically similar performance numbers as you have at EDR in InfiniBand, right? So and then of course you have to bridge between the two fabrics, and so we have this so-called booster interface nodes in between. You can basically forget about these if you're a programmer, since, well, this is just a technical measure in order to bridge between the two fabrics. And well, actually they had a different function in DEEP, which was to act as a kind of host system in order to boot the KNCs. Once the KNCs were booted, so they could act fully autonomously. So this was the hardware setup that we had there. And so partner at that time was Eurotech, so Italian company. And so they provided some standard Aurora cluster. So this were their technology at that time for the cluster side. And then within the project, we developed this booster technology where we put KNCs and XTOLs nodes into this XTOL fabric. So on this side, we had 384 KNC processors sitting in their own fabric. Okay, so what does this mean for applications? So this might be more interesting for you. So starting with this hardware architecture, so as an example, this is one of the applications we had in the project. It was from Cyprus Institute, and so a climate simulation. And the idea behind their simulation is that you have a standard weather model, and then you are interested in what is the interaction of this weather model or climate model with atmospheric chemistry. So then we analyzed the code and found out, well, the most suitable way to put this application on this heterogeneous architecture is to put the base model, so the standard weather model, on the cluster side, and to put the model with the atmospheric chemistry on the booster side. So and then basically both sides run more or less independently for some time, and then they exchange data. So the chemistry moved forward in time, and the base model moved forward in time, and then from time to time you have to exchange data in order to synchronize both parts and ensure that they step forward in an appropriate way. And well, we did similar analysis for these applications which are listed here. And so the basic idea in the project was to really install a co-design effort. So to really use the applications in order to define the hardware, and at a later point of time also to evaluate the architecture and its programmability. And so in the deeper we extended these efforts in order to also look at I/O and resiliency, so which were fields which we explicitly excluded in DEEP in order to, well, make the work more doable. Once we were at a certain point of time, so we applied for a kind of prolongation of the project in order to also investigate these fields. So of course, in order to put your application on such a system, you need a quite complex software architecture, and this is what the software architecture in the end looked like. So here on top you see the application, so separated in so-called highly scalable code parts, so code parts which shall run on the booster side of the system, and these less scalable code parts running on the cluster side. And well, at a first glance, this architecture really looks awfully complicated. In fact, it isn't that complicated because, well, if you look at this part and at that part, it's basically the same, right? And it's as on any standard cluster. So you have some compilers. So in fact, we use and then on top of that, this ORM source-to-source compiler developed by Barcelona Supercomputing Center, which introduces this task level of parallelism that we also heard yesterday about from the Star PU guys. ORMS is a very similar approach. Then you have some low-level communication libraries sitting on top of that. This an MPI library, and then you have an application which uses the MPI and the low-level communication in order to run on such a cluster system. And well, basically the same on the booster side. So since this is also a cluster of special processors, so there's some low-level communication, there's an MPI, and you have parts of your code running there. Since we have this heterogeneous architecture, we need some additional components. So you have to ensure that you can do communication between the two fabrics. which actually means if you are able to use the same fabric on both sides, you can forget about that. But nevertheless, so since we had in DEEP 2 different fabrics, we had to introduce some kind of bridging protocol between the two fabrics. You have to extend the resource management a bit, since you have now heterogeneous resources, which are a bit more complicated to handle, but nevertheless, we managed to do that. And then here is on top this OMS offload application, this OMS offload abstraction, and I will come to that later in a separate slide. So, but first of all, let's see how does an application startup actually work on this type of system. So let's assume that you have an application where you have a main part running on a cluster side, and so this is how it starts. So you do an MPI exec, and it uses the MPI in order to start on the cluster side. So which means that now that the application runs off on a number of these cluster nodes, and now so these processes come to the point where they decide that some of the work shall be offloaded to the booster side. So how does this work? Well, they do a collective call and start the highly scalable code parts as a kind of new MPI applications on the other side of the system. And so what's important is that, well, the offloading is not done by a single process, and a single process starts its own part on the booster side, but the approach is that you have that you have a collection of processes which decide together to offload part of their work to the booster side, which means it's a collective operation here, and it starts a collective application on the booster side. So so the offloading is going to different booster nodes at the same time, and since this is MPI, it even sets up an MPI communicator amongst these processes, so which means that these processes can talk to each other. Sounds complicated. In fact, it's if you look into the MPI standard, it's pretty easy, because this MPI call is already there since sometimes in the 90s when MPI 1.1 standard was defined. It's called MPI com-spawn, and it allows a selection of processes sitting in one communicator, which might be the MPI com-world on the cluster side, to do the MPI com-spawn call, which creates another MPI com-world on the booster side in our case. And furthermore, so the MPI com-spawn call returns a so-called intercommunicator for the calling processes. And so these newly spawned processes might call MPI get parent in order to get the same intercommunicator. And then these processes can use this intercommunicator in order to talk to each other, right? So this is all you need. So you have a number of processes that can already talk to each other. You start a new bunch of processes which are enabled to talk to each other, and you have this intercommunicator in order to exchange data. So that's all you need in order to do offloading. Again, sounds complicated, but what does it mean to an application developer? Well, you have a cluster with some InfiniBand MPI, you have a booster with an XTOL MPI in the DEEP case, and you have some additional functionality like the MPI com-spawn and the cluster booster protocol. Nevertheless, this cluster booster protocol is just hidden behind MPI, right? So you just have to do MPI calls on this intercommunicator, so you don't have to bother with this cluster booster protocol. But in the end, what you have is just a global MPI over this whole heterogeneous system, right? So you just have to think about MPI as an application developer. Still, what you have to do, of course, is you have to do the analysis in order to find out which part of your code shall run on which side. And then you have to throw in the MPI com-spawn and also this communication operations in order to exchange data between cluster and booster. which is still pretty complicated. So due to that, we introduced this so-called offload abstraction. And what it actually does is that it kind of abuses this OMS source-to-source compiler. Okay. Which and what you then actually have to do is you just have to do some annotation of your code, right? So you put in some pragmas which tell the OMS compiler so which part of your application shall run on which side and which data gets into this part and which data has to get out of this part. And by that, you enable the OMS compiler to introduce the specific MPI calls in order to do the MPI com spawn and the calls in order to exchange the data. Then the OMS compiler creates two parts of your source code, so tears your source code apart, puts it into the compiled pipelines of both parts of the system, and finally creates executables which can run on a cluster side or on the booster side. And you start this executables with MPI exec, and so then within this executable that there's an MPI com spawn, which then starts the executable on the booster side. And then you have some kind of runtime system which does all the magic behind the scenes, so which is able to do actually the MPI com spawn, which sets up the intercommunicator, which enables both parts of the fabric to talk to each other. Okay, so this is what we developed in DEEP and DPR. And so now, so what do we do in DEEP-EST? Well, this is what we ended up in deeper, right? So you have this cluster, you have this booster of many core processors. Well, there is some storage module behind the scenes. But, well, if you're at that point of architecture, you can easily think about introducing more of these modules, right? So until now, we talked about cluster and booster, and we can call these modules. But for example, in Deeper, we also looked into new memory technologies. And so what we introduced there was a so-called NUM, so a network attached memory. So you have some memory directly attached to the fabric. So also a nice feature of Xtol, since it's capable to do something like that. And but without any compute resources, or with only very, very limited compute resources. So no real processor here, so which spares some energy, since you do not need a processor there. But you can share this memory between different nodes. So each and every node can write some data into this memory, and you might use this memory in order to exchange data. A different module you can think about, and this is if you think about high performance data analytics, so HPDA. So you might want to have a specific module which is more appropriate in order to do this data analytics stuff. So maybe included some GPUs or more memory or other specific features which make this module more capable to do data analytics. Or you can think about attaching a kind of a graphics booster to the system in order to do some in situ visualization. So this modular concept is what we want to explore in the DEEP-EST project. So the plan is to set up basically a system consisting out of this data analytics model, an HPC cluster, and this extreme scale booster. So let's first of all forget about these modules, which are possible extensions of this concept. And then you can look at applications which might run in this deeper sense just on the cluster and the booster, but you can think about different applications which make use of this data analytics module, and then if it's existing, using a kind of graphics module in order to visualize the data analyzed. Or you can think about having an application which uses the cluster and the booster and maybe some kind of neuromorphic module. We think about in Jülich outside of the project due to the fact that we are part of the Human Brain project, right? So in order to give a first example on how you could use the system, so we have one application from KU Leuven as a partner in the project called Space Weather. So they look on the influence of the sun to the Earth's atmosphere. So if there's a burst from the sun hitting the Earth, it might kill landlines or satellites near the Earth. And so it's interesting to predict this space weather. And so they were already in the project, in project Deep and Deeper, and what they did there was porting their hydrodynamics software called EICKER to this cluster booster concept. So to split the application to the cluster and the booster. So what they are still missing in the application is to get the input data from the sun. And they want to try to automatize that by some general learning algorithm, which will then run on this data analytics type of system. Okay, so if you have this modular supercomputing, so of course what gets more important here is the orchestration of the system, right? So now you have more modules, more heterogeneous resources. You can think about more workflow-like of approaches in order to use the system. So you have to extend the orchestrator significantly, and so since Jülich moved to SLURM in the meantime, so when we started with DEEP, we were using this Torque-Maui combination, but in the meantime we moved to SLURM. So one important part of the project will be to extend the SLURM resource management system in order to make it more suitable for these type of heterogeneous resources. So this will be one important part of the project. So to summarize, so the DEEP project brings the the key idea behind the DEEP project is to take a new view on heterogeneity. So we introduce this cluster booster architecture, and one key idea actually is that hardware, software, and application shall be jointly developed, so that applications might influence the hardware architecture of the system, and of course the system software is a very important glue between these two parts. So the idea behind all these projects is that it shall be strongly co-design driven. So in Deeper we explored future directions of I/O and resiliency. Have not presented that part, but so for the future our idea is to have this modular supercomputing architecture. So to have this generalized cluster booster architecture with additional modules, and well, one key idea behind that is of course in order to support the convergence between HPC and HPDA, so high performance data analytics. And yeah, what will be important there is this more dynamic resource management. Beyond that, so currently we are doing a first step into more production-like environment in Jülich. So we are currently setting up a KNL-based booster that will be attached to the Eureka cluster. So we say by end of the year we will have the first production cluster booster system. So in real production. And well, our idea in Jülich is that there will be more modules to come, especially in the context of the Human Brain project. So that's it from my side. Are there any questions?